Hi folks! The following video talks about ethers and epoxides. I'll be discussing their structures, how to prepare these molecules, and their reactions. In terms of their structure, ethers contain an oxygen bonded to two different carbon groups. Ethers can be classified as either symmetrical or unsymmetrical. So as an example of a symmetrical ether, this is an ether oxygen connected to two different ethyl groups. So because the oxygen has two of the same substituent, we would call it symmetrical. Alternatively, ether oxygens can also be attached to two different carbon groups. So on the left, there's one with a methyl and an ethyl substituent. And then furthest to the right, there's an example of an ether with a phenyl and a propyl substituent. Because these ethers contain two different carbon groups, they are classified as unsymmetrical ethers. In terms of their physical properties, compared to alcohols, ethers have relatively low boiling points. Because they do not contain polar OH bonds, ethers cannot hydrogen bond with themselves. However, because they do contain oxygens, ethers can serve as hydrogen bond acceptors in the presence of something like an alcohol or a carboxylic acid, something with a polar bond to a hydrogen that can be donated in hydrogen bonding. In samples of themselves, ethers interact with each other with dipole-dipole interactions. Here's an example of the solvent THF, tetrahydrofuran. This is a cyclic ether structure. This molecule contains a dipole moment pointing toward the electronegative oxygen end of the molecule, and two of these cyclic ethers could interact with each other by aligning their dipoles, placing the partial positive charge of one molecule close to the partial negative end of the dipole of another molecule. When talking about preparing ethers, I want to review a couple of methods we've already learned for preparing ethers and then introduce a new method. One way that we've already seen to prepare ethers is by acid-catalyzed addition of an alcohol to an alkene. In this mechanism, a carbocation intermediate is generated, so be on the lookout for potential carbocation rearrangements. As an example of this method, you would be treating your alkene with H+ or H2SO4 in the presence of an alcohol solvent. A carbocation would form, the alcohol solvent would act as the nucleophile, and after a deprotonation, there's a new carbon-oxygen bond in the molecule, and notice this oxygen is attached to two different carbon groups, making this an ether product. In this particular example, this acid-catalyzed addition generated a new chiral center, so I drew both enantiomers of product. Another method for preparing ethers from an alkene is oxymercuration demercuration, here as well using an alcohol as the nucleophile. This set of reagents is desirable if you do not want a carbocation rearrangement to occur. What this would look like is treating an alkene with two steps of reagents. First, mercury acetate in the presence of an alcohol, and in the second step, treatment with NaBH4, which removes the mercury. This is a Markovnikov addition of the alcohol minus its proton to the more substituted carbon of the alkene. Carbocation rearrangement does not occur, and in this particular example, a new chiral center was generated, so I drew both stereochemistries at that new chiral position, where that new ether is present. A new method that's useful for preparing ethers is called the Williamson ether synthesis. The Williamson ether synthesis combines an alcohol and an alkyl halide to generate an ether. The way this is performed is you start with the alcohol, treat it with a strong base like sodium hydride, and then in a second step, treat the intermediate with an alkyl halide. This has the effect of converting the alcohol oxygen into an ether. An example of what this could look like is treatment of here ethanol with sodium hydride, followed by treatment with bromopropane. And in my product, the ether oxygen has the original ethyl group, and it is now connected to that propyl group that was formerly the alkyl halide. The mechanism for the Williamson ether synthesis starts with a proton transfer. The sodium hydride serves as a strong base that can deprotonate the alcohol. This first step generates an alkoxide, the conjugate base of the alcohol. Then in the second step of the reaction, this alkoxide is treated with the alkyl halide. The alkoxide is a good nucleophile and a good base, but this is a primary alkyl halide, which will favor an SN2 reaction. So I'll bring in the oxygen nucleophile and kick out the leaving group in the same step. And this would generate the final ether product, where the carbon that's attached to the oxygen of the ether is this carbon that was formerly attached to the halide. In order to have a successful Williamson ether synthesis, you should use a strong base that can deprotonate the alcohol. Two common ones are sodium hydride or NaNH2. And because an SN2 reaction occurs at the alkyl halide, the alkyl halide should be a methyl halide or a primary alkyl halide. If a secondary or tertiary alkyl halide is used, E2 is favored rather than SN2, so the desired substitution reaction will not take place as the major product. As an example, let's consider you're given the following ether, and you want to choose the reagents that should be used in order to prepare the ether in the highest yield possible. On the left side, I have a cyclohexyl substituent, and on the right side, an ethyl substituent. What you would want to do is look at the substitution of the carbons attached to the ether oxygen. Notice on the left I have a secondary carbon, and on the right I have a primary carbon. For the synthesis to be efficient and high-yielding, I want the primary substituted group to be the alkyl halide, and then I will use a secondary alcohol as my starting material. So what my efficient synthesis would look like is starting out with cyclohexanol, treating it with a strong base sodium hydride, followed by bromoethane, and this would generate the desired ether in the highest yield possible. If I'd reversed this and made the cyclohexyl group the alkyl halide instead, this synthesis would not be efficient because you cannot perform SN2 reactions efficiently on secondary alkyl halides. Now I want to turn our attention to epoxides, which are a certain class of ethers featuring an oxygen in a three-membered ring with two carbons. One method that we've already seen for preparing epoxides is treating alkenes with RCO3H. This has the effect of converting the alkene carbons into the carbons of the three-membered ring of the epoxide. And RCO3H is a peroxy acid. And RCO3H is a peroxy acid. Sometimes instead of RCO3H, you'll see it written as MCPBA. This is simply a particular type of peroxy acid. In terms of preparing epoxides, we need to consider stereochemistry, because the epoxide stereochemistry is going to reflect the stereochemistry of the alkene starting out. Treating a trans alkene with a peroxy acid will generate two stereoisomers of product, each of which has trans stereochemistry. So the way I've drawn these epoxides, the three-membered ring is in the plane of the page, and to show trans stereochemistry, I draw the R groups as either a dash or a wedge. I have another enantiomer of product where I have the wedge on the left and the dash on the right instead, but notice both of these products have that trans geometry. And similarly, if I had started with a cis alkene instead, treatment with a peroxy acid would generate a cis epoxide, where I've drawn the epoxide again in the plane of the page, and then both of the R groups as wedges. This is a meso compound, so it is the only stereoisomer that's formed. Another method for generating epoxides is from a halohydrin intermediate. Recall that halohydrins have a halogen and an OH group on neighboring carbons, and we generate these from an alkene. Here's an example of cyclohexene being treated with bromine in the presence of water. You would form a halonium ion with the bromine, and then the water would serve as the nucleophile in the nucleophilic attack step. Ultimately, you end up with an anti-addition, where the halogen and the OH group were added from opposite faces of the alkene. The way you form an epoxide from a halohydrin is you treat it with a base. This could be sodium hydroxide, or it could be sodium hydride, or NaNH2. And this has the effect of deprotonating the oxygen and causing a substitution reaction that ultimately forms the epoxide. So, from the halohydrin intermediate, the mechanism begins with a proton transfer. In this case, hydroxide serves as the base to deprotonate the alcohol group. This generates the conjugate base of the halohydrin. This anionic oxygen within the molecule is a nucleophile, and this carbon of the alkyl halide adjacent to it is an electrophile. An SN2 reaction can occur, where you bring in the nucleophile to the electrophilic carbon and kick out the halide leaving group in the same step. And this intramolecular nucleophilic attack forms the three-membered ring of the epoxide. For the remainder of today's video, I want to talk about ring-opening reactions involving epoxides. First, I want to consider reactions where you're treating the epoxide with a strong nucleophile. As an example of this, let's consider an epoxide being treated with sodium hydroxide. The OH- of this is a strong nucleophile, where by strong I mean typically anionic. In the first step, I would treat the epoxide with the strong nucleophile, and in the second step, I would treat it with water. This causes a ring-opening reaction of the epoxide where the nucleophile was added to the epoxide. So let's consider the mechanism for this reaction. The carbons of the epoxide are electrophilic, and I'm adding in a strong nucleophile. The first step of the mechanism is going to be a substitution reaction, where I'll bring in the nucleophile to the carbon of the epoxide and break its bond to oxygen in the same step. This generates a new carbon-oxygen bond, and the oxygen of the epoxide is now only connected to the other carbon, and it is now anionic. To get to a neutral product, I need to protonate this anionic oxygen, and to do this I'm going to bring in water in a second step. I'll use the anionic oxygen as a base in the proton transfer step to deprotonate water, which is serving as an acid. And this generates the neutral ring-opened product. This ring opening in the presence of a strong nucleophile works for other strong nucleophiles other than hydroxide as well. So for example, if an alkoxide had been used as the nucleophile, a ring-opening reaction would still occur, where the oxygen of the alkoxide was added as a nucleophile, generating a new ether group in the product. If a cyanide anion had been used as the nucleophile, a new CN triple bond would be present, added to one of the carbons of the epoxide. Sulfur nucleophiles could work as well. This would generate a new carbon-sulfur bond in the product and open up the ring. Acetylide anions, the conjugate bases of terminal alkynes, can serve as the nucleophile. This generates a new carbon-carbon bond. And last, a source of a hydrogen nucleophile is LiAlH4. The aluminum-hydrogen bond in this molecule can serve as the nucleophile, and this also opens up the epoxide ring, adding a hydride nucleophile. So far, I've only shown you examples where you had CH2 groups on both of the carbons of the epoxide, where regiochemistry didn't matter. However, if you have substituted epoxides, you will have to consider regiochemistry. And with strong nucleophiles, nucleophilic attack will occur at the less substituted carbon of the epoxide. This is a steric effect. The strong nucleophile prefers to add into the carbon that is less substituted because there is less steric clashing at this position. So let's consider we're adding a strong nucleophile to this following epoxide. Notice one of the carbons has 2 methyl groups on it, and the other carbon of the epoxide has only hydrogens. Based on sterics, the strong nucleophile will prefer to add to the CH2 position of this epoxide. In the product of this ring opening reaction, the nucleophile would be added to the right carbon, and the oxygen of the epoxide ends up attached to the more substituted position, as this tertiary alcohol group on the left. In terms of stereochemistry for epoxide ring opening reactions, anti-addition is going to occur, and there will be an inversion of stereochemistry at the carbon that's undergoing nucleophilic attack. Here, let's consider the following epoxide. This carbon of the epoxide is tertiary, whereas this one is secondary. The strong nucleophile will preferentially attack the less substituted carbon of the epoxide based on sterics. So in the product, the nucleophile would have added to this less substituted position, and the oxygen of the epoxide ends up at the more substituted position. Notice that the OH group and the new nucleophile are anti to each other. Notice that there has been no change in stereochemistry at the carbon position of the epoxide that was more substituted and was not attacked by the nucleophile. But the carbon of the epoxide that was attacked by the nucleophile had an inversion of stereochemistry. That carbon had a wedge bond to an oxygen starting out, and then the nucleophile added opposite this, so the new carbon nucleophile bond is a dash in this case. Now I want to consider ring opening reactions of epoxides that occur under acidic conditions instead. These will involve treatment of the epoxide with an acid. This could be written as either H+ or H2SO4. And this will occur in the presence of a weak nucleophile, such as water or an alcohol. This ring opening reaction involving a water nucleophile would generate a diol product. You previously saw this reaction back when I talked about anti-dihydroxylation, but I want to review it here because it differs from what I just showed you for strong nucleophiles. So under acidic conditions, the first step of the ether ring opening mechanism is going to involve a proton transfer. The oxygen of the ether is going to serve as the base, and in this case, H3O+ is the acid. This is the actual acid that's present when you dissolve sulfuric acid in water. This proton transfer generates the conjugate acid of the epoxide, and this makes the carbons of the epoxide even more electrophilic. Making these carbons more electrophilic is important for promoting nucleophilic attack by a weak nucleophile such as water. The water is going to come in as a nucleophile, and the carbon-oxygen bond of the epoxide will break, in an SN2 type step. The oxygen of the epoxide is now only attached to the carbon on the left of the epoxide, and that oxygen is neutral. The oxygen of the water molecule that added is now cationic, and it's attached to the other carbon that was formerly a part of the three-membered ring. To get to a neutral final product, I need to deprotonate the cationic oxygen under acidic conditions in water. Water itself is the best base, so I'll use water as a base in this proton transfer step. And this deprotonation would get to the final neutral product. So I recommend going back in your notes to where I talked about strong nucleophiles and compare the mechanism that I just drew under acidic conditions to the one I drew previously for strong nucleophiles. Notice how these mechanisms differ. There are other variations of these ring openings under acidic conditions as well. So for example, treatment of an epoxide with HBr, the H of this could serve as the acid and the Br could serve as the nucleophile in the ring opening reaction. Or alternatively, you could use an acid catalyst in the presence of an alcohol solvent, and in that case, the alcohol would serve as the nucleophile instead of water, ultimately generating an ether group in the product. The regiochemistry of epoxide ring opening under acidic conditions is different from what we saw for strong nucleophiles. Under acidic conditions, the nucleophile will attack the more substituted position of the epoxide. So let's consider we had this differently substituted epoxide where one carbon has two methyls and the other carbon just has two hydrogens. This is being treated with an acid catalyst in the presence of a weak nucleophile, such as a neutral solvent molecule. Under acidic conditions, the nucleophile will preferentially add to the more substituted carbon of the epoxide, in this case the one on the left. In the product, you'll have a new carbon nucleophile bond at the more substituted position, and the oxygen of the epoxide will be present as an alcohol group on the less substituted carbon. The nucleophile preferentially adds to the more substituted position due to the fact that adding the nucleophile to this carbon puts partial positive charge on a more substituted carbon at the transition state, which is favorable. In terms of stereochemistry, anti-addition will still occur, meaning there is an inversion of stereochemistry occurring at the carbon that's being attacked by the nucleophile. In this case, though, a weak nucleophile. Let's consider a chiral epoxide, where one carbon is tertiary and one carbon of the epoxide is secondary. Under acidic conditions in the presence of weak nucleophiles, the nucleophile will preferentially add to the more substituted carbon of the epoxide. In the product, this more substituted carbon will have the new bond to the nucleophile, and the oxygen of the epoxide is present as an alcohol on the less substituted carbon. Notice that the nucleophile and the OH group are anti to each other in this product. At the more substituted carbon, where you formerly had a wedge bond to an O, the methyl group that was formerly a dash is now a wedge, and the nucleophile is a dash now, meaning there has been an inversion of stereochemistry at this carbon that was attacked by the nucleophile. At the less substituted carbon, where you previously had a wedge bond to O, that wedge bond to O is maintained, meaning there has been no change in stereochemistry at this position because the nucleophile did not attack that less substituted position. Alright, so in summary, today's video talked about ethers and epoxides. I talked about 3 methods for preparing ethers, including a new method known as Williamson ether synthesis. I also talked about epoxides and their stereochemistry. 2 ways to prepare epoxides, including a new way involving a halohydrin intermediate. And then I talked about ring openings of epoxides, either using a strong nucleophile or under acidic conditions with a weak nucleophile. These reactions have different mechanisms and have different regiochemical outcomes. That's it for this video. I will see you in class.